Now let's talk about sampling and aliasing. And let's start off by looking at a problem. So let's say I take some samples. I'm taking 5 samples per second, and the samples I get are the green dot here, 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 and here. Okay? And then I wish to reconstruct the signal that produced those samples. So the question then, is it the 3 Hz signal, the blue one, that produced those samples, or is it the 13 Hz signal that produced those samples? That's the red line. Well, the answer is, could be either one. Or actually, there's an infinite number of signals that could have produced this particular set of samples, okay, or frequencies that produce this set of samples. Because notice what happens here. At this sampling rate, and I'm not claiming that it's always 3 and 13. I'm saying 3 Hz and 13 Hz when you have a sampling rate of 5 samples per second. Notice what happens here. When I take, here's my first sample. Of course, they both be at the same spot if they're cosines, right? Because they start up here. But at 5 samples per second, then the second sample will be at 0.2 seconds. So we look right here and we say, okay, right here, let's move up until we hit the line. Well, we're hitting both lines at the same amplitude right here. Looks like it's a little bit below the minus 0.75. Now, if I changed it to 6 samples per second, which means this would still be the first sample, but now the second sample would be over here because we're squeezing in more samples, right, in this 1 second period. Let's say it was right here. Well, that means when we move up, I'd hit the blue line here, but the red line's up here, so there's no ambiguity between these 2 frequencies. There still would be other frequencies where we could potentially have that problem, but not between these 2. But once again, the issue here is that when I take this sample right here and get this value, it could have came from either the red line or the blue line. So when we have a sinusoid of frequency f and a sampling frequency of s of s, then the aliases of the original signal will be signals with this frequency, f plus or minus capital N times f of s, where n is 0, plus or minus 1, plus or minus 2, and so forth. So what that is saying here is that 13 Hz is an alias for 3 Hz, and also 3 Hz would be an alias for 13 Hz when the sampling rate is 5 samples per second. As I stated earlier, if I were to change this to 6 samples per second, then they wouldn't be aliases. There would be other aliases. So here's an example. Let's say f is equal to 2 Hz and fs is 5 Hz. Well, then 7 Hz is also an alias for 2 Hz, 12 Hz is an alias, 17 Hz, and an infinite number of other frequencies. All right? Aliasing is something you've actually encountered before, because when you watch a video or movie and you see a wheel turning backwards, that's actually an example of aliasing. Let's see an example of what I'm talking about there. So let's say we have this wheel. And we'll put this line on there to make it clear where we're at. And there's a dot right here, right? And the wheel turns counterclockwise. So it goes right here. So let's say we take a picture of it at this point in time. And then the next time I take a picture, the dot has rotated here. So I'm taking pictures at the rate of 3/4 of a revolution. That is, the wheel turned all the way around to this point before I took another picture. So I take a picture. And then I continue on, and now we moved all the way around and the dot's here. The next time around, the dot is here. Next time around, the dot is here, and so forth. So I took a snapshot, 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 snapshot. But if I play those images back to you like I would in a movie, what do you see? You see the wheel with the dot here, and then you see the dot, then you see the dot, then you see the dot, and so forth. So it looks like it really was going this way. So the problem is aliasing, because the rate at which the wheel is turning and the rate at which I'm taking these images are related. That's what's happening here. right? So why is that a problem? Well, it's a problem because remember we took these samples because we couldn't record the entire continuous time signal. But with these samples, we wish to reconstruct the original signal. So we go back to here and we say, okay, let's say it really was a 13 hertz signal, and I took this sample, this sample, this sample, this one, this and this one. But we didn't know that it was a 13 hertz signal. We said, okay, given these green dots, which are the samples, reconstruct the signal that they came from, or the cosine wave they came from. Well, because there's an infinite number of possibilities, I have no way of knowing which one of those they are, short of there being some other factors. So what can we do about it? Well, there's a couple of things that are done in practice. One is to pass through what's called an anti-aliasing filter before you start taking the samples. And what it does is eliminate frequencies beyond some range. Okay? And then the other thing you can do is use a sampling rate that's sufficient to reproduce a signal. Remember in an earlier video when we were first talking about sampling, and I used, I think it was a 3 hertz signal, but we only had 2 samples in that entire time period. Well, it was easy to see that I wasn't sampling fast enough to really represent the underlying signal. So how do we answer these two things, or that is, how is this done? How do we know what the sampling rate is? Before we look at the second question, let's talk about how the first one's done. And so an anti-aliasing filter uses what's called a low-pass filter. And let's see what I mean by that. So there's a number of standard filters. And so for a low-pass filter, which in the future I'll probably just write LPF, it has what's called a frequency response. That looks like this. In the ideal case, you won't really be able to achieve something that looks like what I'm about to draw, but it's theoretical. So typically we would have, say, 1 right here, but it doesn't necessarily have to be. But this right here is the amplitude. And over here is the frequency. And so this function that I'm plotting here is a function of frequency. So when we're talking about a low-pass filter, it has a frequency response that looks like this. So what it says is that if I have a signal, S, which is composed of frequency F1 plus F2 plus F3, well then for those that are between 0 hertz and F sub C, the cutoff frequency, they get multiplied by 1. And for anything to the right of FC, it gets multiplied by 0. So let's say that what we had here was FC was 50 hertz. And we'll say our signal here was 13 hertz plus 27 hertz plus 68 hertz. Well, 50 is here, 25, say 27 is about here, 13 is about half of that, so it's roughly here, and 68 we'll say is here. So if we have what passes through the system, we end up multiplying 13 by 1, so we get all of 13 again. 1 times 27, we get all 27 again, but 68 is multiplied by 0, so that means what comes out of my filter, we'll call this S sub 1, then S sub 2, the output, will be a 13 hertz signal plus a 27 hertz signal, and we get rid of this. So the reason for that is that if you don't want certain frequencies, and remember when we looked at those, at the possible aliases, we had lots of frequencies that we could have. Well, by having the low-pass filter, you're saying, I won't even let this even be present before I start taking samples, therefore I can't be recording from it. If it's not there, if the 68 is not there, I can't be taking samples from a 68 hertz signal. Okay, so that's how that works. So what about the other question? That is, what's the sampling rate we should use? Well, for this we use what's either sometimes called the Shannon sampling theorem or the Nyquist Shannon sampling theorem. But basically what it does is state that in order to reconstruct our original signal from our samples, the sampling rate needs to be greater than twice the highest frequency present in our signal. Okay? So if going back to what I just showed you, if I decided that, 30 hertz would be the highest frequency present that I want to record that would make it past my anti-aliasing filter, okay? Well, then 2 times 30 would be 60. It says I should be sampling at least 60 samples per second. And in practice, people often will oversample, so they would take more. So once again, you somehow need to know, and it depends on what you're doing. If I'm recording music, it has certain ranges of frequencies, right? For certain musical instruments, a human voice has certain frequency ranges. So you have to have some idea of what it is you're attempting to record or take samples from. But then whatever the maximum frequency is that's present, multiply it by 2 and then sample at a rate that's greater than that. If I take this expression and rearrange it by dividing both sides by 2, then we can get what's called the Nyquist limit, which says that the highest frequency in the signal that you would be able to deal with without there being any aliasing should be less than half the sampling rate. So if I say I'm going to sample at 1,000 samples per second, then in order to avoid aliasing, you wouldn't want the highest frequency to be greater than just under 500 hertz per second, right? Or 500 hertz, excuse me. Now, one note of caution. I've noticed in reading that some authors use the term Nyquist limit, Nyquist rate, and Nyquist frequency interchangeably. So they treat them as synonyms. Some authors don't. They treat them as different things. So that's another thing you just have to be careful of when you're trying to study signal processing.